some of the notations which you'll be looking at or which you'll be using in the course of this class on real analysis is the semicolon, or this symbol which we call such that. The symbol written like this, there exists. When we have this, we say it refers to defines, and then the V with the slash refers to for all. We are familiar with this from our knowledge of set theory in elementary mathematics. We have it referring to element of or belong to. This with the slash referring to not element of, and then this which we call epsilon, and then the ellipsis. We will begin by giving a definition to what we call a sequence. Sequence. You will remember from our elementary maths that when we are talking about a sequence, we say that what? A sequence can be described, a sequence can be described as a set of numbers, say u1, u2, u3, in a definite order, of arrangement, which corresponds with natural numbers and formed according to a definite rule. That is a sequence. A set of numbers in a definite order of arrangement corresponding to natural numbers and formed according to a definite rule. Each number in the sequence or of the sequence, each number of the sequence is called or referred to as the term of the sequence. So my u1 now is the first term. My u2 will be what? The second term. u3 will be what? Third term. And if I continue like that, I can get a un, which we refer to as what? The nth term of the sequence. A sequence can either be finite or infinite. Let's put that down also. A sequence can either be finite or infinite depending on the number of terms in the sequence. A sequence can either be finite or infinite depending on the number of terms of the sequence. That tells us that a finite sequence will definitely have finite number of terms, and an infinite sequence will do what? Have infinite number of terms. They are sequences that have finite number of terms and our infinite sequence are sequence with what? Infinite they are sequence with infinite number of terms. For example, let's look at this sequence. Consider the sequence 2, 7, 12, 17 down to 32. Looking at this sequence, based on what I said here, where I said each number of the sequence is called the term, and that my U1 is the first term, my U2 the second term, U subscript 3, we call that the third term. Then what happens here? The first term, U1 of the sequence is 2. The second term, U2 of the sequence is 7. And I have a last term in that sequence, L, which is what? 32. This tells me that that sequence is what type of sequence? It's a finite sequence. It's a finite sequence. And the nth term of the sequence, the nth term of the sequence is given as what? If you take a closer look at this sequence, you see that it is an arithmetic sequence. So my nth term, UN, is given as A plus N minus 1 into D, and that is what? 2 plus N minus 1 into 5, and that gives us what? 5N minus 3. That's the nth term of the sequence. That is a finite sequence. Let's look at an example for the infinite. Consider the set of numbers 1, 1/3, 1/5, 1/7. If you look at this sequence, because I can see the ellipses here, I know it is what type of sequence. It is an infinite sequence because it has no end term. Therefore, our concern majorly for this real analysis is centered on what? Sequences of real numbers, which are majorly going to be infinite. Majorly going to be infinite. Now, a formal definition for sequence now, a formal definition for sequence will be what? Formal definition for sequence will be what? A sequence of real numbers we represent our real number like that, is a function defined on the set of natural numbers. A function, let me quickly wipe this off. A sequence of real number is a function defined on the set of natural numbers whose range is contained in the set R of real numbers. That would be a formal definition for a sequence. A sequence of real number R is a function defined on the set of natural numbers n, where our n is from 1, 2, 3 to infinity, whose range is contained in the set R of real numbers. Alternatively, we can say a sequence of real number exists when there is a map of natural numbers, a map of natural numbers n into real numbers R, into real number R. That means my sequence Xn can be defined such that it's a map from natural number to set R of real numbers. It's a map from the set of natural numbers to the set R of real numbers. Now each term of the sequence is a mapping. Each term of the sequence is a mapping from the set of natural numbers to what? The set of real numbers. To the set of real numbers. Now, how do we denote? How do we denote sequence? How do we denote sequence? Remember, we have said in real analysis, our major concern is what? Infinite sequences. How do we now denote this sequence? Given the sequence Xn or the sequence A subscript n, or X subscript n, which actually refers to what? My Xn can be defined as what? The set of elements x1, x2, down to what? Xn, or my sequence An can be defined as what? A1, A2, down to An. Now, a simpler way of writing this is to just write my xn in brackets, or write my xn such that n is an element of the set of natural numbers, or I write it as what? Xn, where n element of that, or I write it as xn, where n is from 1 to infinity. And if I don't want to use this type of bracket, I can make use of the curvy bracket which we are used to in set theory, the curvy brackets to denote my set. However, the best way to define a sequence is by writing down the general rule or general term for that sequence. Let's look at the following examples of sequence. Let's look at the following examples of sequence. Examples of sequence. The first example we'll be looking at consider the sequence xn defined as follows: minus 1 raised to power n, where n belongs to the set of natural numbers. The elements of this sequence are what? When n is 1, we have minus 1. When n is 2, we have 1. When n is 3, minus 1. When n is 4, 1. When n is 5, minus 1. When n is 6, 1. And it continues like that. This can be written as what? Minus 1 raised to power n, as n moves from 1 to infinity. You can visualize this on the number line. You can visualize this on the number line as follows. Let's look at our number line. The elements of the set, of the sequence rather, starts from minus 1, jumps to plus 1, jumps back to minus 1, jumps back to plus 1, and it continues to move like that. If it is on the real, on the xy plane, if you visualize it on the xy plane, how does it look? On the xy plane, we have it as what? That's our plus 1, that's our minus 1. When x is 1, it's moving from what? Minus 1, and then to 1, jumps back to minus 1, and then back to 1, and then to minus 1. You can see the movement of the elements or terms in the sequence. But our concern now goes to what will it be as n grows bigger and bigger, as n tends to infinity? What will happen to this type of sequence? Let's look at another sequence and see if that too will go in like pattern. Consider the sequence of reciprocal of numbers. the sequence of reciprocal of numbers. My sequence AM for that will be defined as what? 1 over n, where our n belongs to what? The set of natural numbers. What are the elements of this sequence, or the terms of this sequence? I have 1, 1 over 2, 1 over 3, 1 over 4, and it continues like that. If I visualize this on the XY plane, if we visualize it on the XY plane, what do we observe? On the XY plane, we can see that as our n is increasing, the terms of the sequence is drawing closer and closer to 0. Is drawing closer and closer to 0. Let's look at another example. Let's look at another example. Consider the sequence of reciprocals of even number. Reciprocals of even numbers. Let that be our sequence YN. And how do we define that? Now we define as what? 1 over 2 to the power n, such that n also belongs to what? Set of natural numbers. We are talking about the sequence Yn being the reciprocal of even numbers. What will be the elements or the terms of this sequence? The terms of our sequence Yn would then be what? You can take a look at it and begin to think what is happening to that sequence as n grows bigger and bigger. Our Yn, sequence Yn, the elements or terms in the sequence will be what? 1 over 2, 1 over 4, 1 over 8, 1 over 16, and it continues like that. Again, if we visualize this on the two-dimensional plane, what is happening? As our n, the small n, is getting bigger and bigger, we can see that the elements of the sequence or the terms of the sequence are moving closer and closer to 0. Moving closer and closer to 0. You can try your hands on the following sequence and determine what happens to the terms of the sequence as n gets bigger and bigger. Determine what happens to the following sequence as n gets bigger and bigger. The sequence xn defined such that 1 plus minus 1 is raised to n. The sequence un defined such that minus 1 raised to power n is divided by n. The sequence xn defined such that 1 is divided by n into n plus 1. And lastly, the sequence zn defined as what? 1 over n squared plus 2. Try your hands on the following sequence. Bring out the terms of the sequence and let us know what happens to the sequence or to the terms of the sequence as n gets bigger and bigger. In the next class or in the next video, we'll be looking at what we call the limit of a sequence. If you have benefited from this video, or if you have learned one thing or the other from it, give the video a thumbs up and share with your friends and colleagues. Have a beautiful day. God bless you.